right. Now we're moving on to part 2, which is about blood vessels. So here are your objectives for blood vessels. First, we're going to overview blood vessels and what they do. Then we're going to take a look at arteries versus capillaries versus veins. How does blood move around, and some capillary exchange. So, how do we name blood vessels in the systemic circuit? You don't need to know what the systemic circuit is. It's one of the biggest circuits of vessels, blood vessels in the body that carry blood from the lungs down to any tissue of the body, right? From your toes down to the toes, and some of it goes up to your tippy top to feed your hair cells, right? So that's a systemic circuit. It goes systemically all over the place to the different tissues. How do we name the blood vessels in this circuit? And so I'm gonna just briefly go through it now, but there's little nuances that we'll see in the heart section if it's a different type of circuit, okay? So arteries, they pump blood away from the heart. So this is true for any circuit. A is away, okay? That's my trick to knowing that arteries are pumping blood away. That's how you name an artery, okay? Arteries pump blood away. So here's the heart, let's say, right? Let me put the heart over here. Blood moves only in one direction in the heart, okay? So let's say that over here, here's my blood vessel, and the blood is moving in this direction. It never turns around in the other direction. Blood going in this direction, this would be an artery because blood is flowing out of the heart. A is going away from the heart. And then we end up going down the artery, right? We go to the arteriole, to the and then even smaller vessels. Arterioles are smaller arteries that are branching and becoming much smaller, right? As you get closer to your tissues, that big artery is going to get smaller, smaller, smaller and become arterioles. And then they will become capillaries, okay? So the capillaries, these are the smallest vessels where oxygen and nutrients will exit. So over here at the capillaries, the whole point of bringing blood to the cells, let's say these are the cells over here, right, of your toes, right? These are little toe cells with their little nuclei. Or let's say they're hair cells at the top of your head. I want you to think of this as being anywhere because they do go everywhere. There are capillaries in many locations to feed all the cells of your body. So the heart sends blood down an artery, down the arterioles, into the capillary. Sometimes they call it the capillary bed because it's like a bed full of little vessels. And they feed the cells. So capillaries, they're the smallest vessels. And this is where oxygen and nutrients exit. So oxygen and nutrients will exit out and feed the cells over here, right? They will give oxygen and glucose to these cells. Remember, they need that fuel and oxygen to make ATP. If not, they die and they necrose and they will not be alive. So we feed those cells, and at the same time in the capillaries, all this junk, CO2 that it makes as it's making ATP, the CO2 will return into, and any waste will return into the blood. And this is why we put these colors, the red and the blue, because red is oxygenated blood and the blue is trying to show deoxygenated blood full of CO2 instead, right? And so this will, with the waste, will return via a venule. Venule sounds like a smaller vein, venule. It sounds smaller, cuter. So it will go from the capillaries to the venule, and then it will go to a vein, right? And it'll return back over here, back to the heart, right? It'll return actually on this side, but we don't need to go through those logistics right now. It'll return to the heart, and it will bring back the blood, right? It's going back to the heart. So a vein pumps blood towards the heart, right? So it is going back towards the heart. Il revient au cœur. Venir au cœur, right? V is for coming back to the heart. Reviens, venir au cœur. So veins bring blood back towards the heart. Okay, so that's the idea for these loops. Now, I'm just gonna say this once, and if it doesn't make too much sense, don't worry, because we're gonna revisit this concept. I want you to be careful when you're naming arteries and veins, because the pure definition of an artery is it brings blood away from the heart, and a vein will bring blood towards the heart, right? So arteries do not always carry oxygenated blood. In this case that I'm showing you here, yes, the arteries that are going away from the heart, they are bringing oxygenated red blood to go feed the tissues. But there is a case with the lungs where we send deoxygenated blood to the lungs, and that is still an artery because it's going away from the heart. So I want you to be careful and not name arteries based on if it's red or blue, if it's oxygenated or deoxygenated. It doesn't always work. You need to name them based on if they're going away from the heart or back towards the heart, okay? So same thing here. Veins do not always carry deoxygenated blood. They're not always blue, deoxygenated. In the case of the lungs, it would be different. It would be oxygenated blood coming back to the heart. And we're going to see this in a bit. I just wanted to put this caution note because it's one of the biggest misconceptions, and you will have some difficulty with that in the beginning. So over here, how do we name blood vessels in the systemic circuit? Again, this is the systemic circuit. So it makes sense that the red blood, the oxygenated blood, is the arteries, and the returning blue blood is the veins, right? But remember, caution, we do not always carry oxygenated blood in arteries, and we do not always carry deoxygenated blood in veins. There's an exception in the lungs. We're going to see this later on. This is the systemic circuit, right? It's going to the tissues, right? When we go to the lungs, we're going to see it's a bit different. So that being said, put that to the side, right? How do we name the blood vessels in this circuit? Arteries carry blood away from the heart. So here we see this, we would call this an artery. As we get smaller, we call these arterioles. These are the smallest arteries, right? And then we get to the capillaries. These are the smallest blood vessels, and they facilitate gas, nutrient, and waste exchange between here and whatever cells are around, right? Maybe we should draw a few cells here to show that there's maybe your toe cells that you're feeding over here, right? You're bringing blood to them. You're exchanging substances over here with them. And then all the bad blood comes out through the venules, right? Small veins, and then up veins towards the heart, right? They carry blood towards the heart, and they enter back to the heart, okay? Now I want to talk about pressure, right? And where pressure is coming from. I want you to imagine a water balloon, right, with a long straw coming out, very long straw. When you squeeze the water balloon, right, eventually you build up enough pressure such that the water gets forced out of the water balloon into the straw, right, and it will exit the vessel. I want you to think of the water balloon as the heart and the straw as a vessel, okay? So the heart is what generates a pressure to push the liquid, right, the blood out of this circuit. So in this case, right, you squeeze the heart pumps and squeezes like the water balloon, you squeezing the water balloon, and that pushes it only in one direction. It pushes blood out of arteries, and the arteries go down, and go all the way through, right? I like to think of this like a garden hose too. You turn the tap on, right, and water rushes out of the tap and pushes through and goes out of the hose, right? Now, I want to talk about pressure. Where is pressure the highest in all of this? if you turn on the tap, right, and you actually cut your long, pretend it's a long garden hose, right? And you look at the hose at the end dribbling, and there's just a few drops coming out, right? The pressure is very low at the end, right? But if I cut the hose maybe a bit earlier on, closer to the source of where it's gushing out, the pressure might be very high there, right? You might have a higher pressure. This is because along a garden hose, right, a very long hose, the high pressure pushing water out at the tap will be very high at the beginning, and as it goes along to the longer end of the garden hose, those ends of the hose will have lost a bit of energy, right? Lost a bit of pressure, and the pressure will be a lot weaker by the time it gets to the end, right? So all this to say, I want you to imagine being a little red blood cell over here, okay? I want you to imagine you, the little red blood cell over here, and the heart contracts and pushes against the liquid. You will feel a very high pressure, a full and high pressure at this area. So the arteries have the highest pressure in all of this system. The arteries will get a kick, a wave from the faucet that turns on, from the contraction of the heart. It will feel the highest pressure. But as you go along, right, in the arterioles, you have variable pressure, medium-ish, right? Over here, you're going to have a medium-ish pressure, and then it's going to get even lower. Lower pressure over here, right? The pressure decreases as you go throughout the system, okay? So that's important for us to know, is that at the beginning, you have a very high pressure, and at the very end of the loop, you have a very low pressure. Just like a garden hose, right? The source of the pressure comes from the heart pushing all the blood out the arteries. By the time it gets to the end of the hose, right, you're not getting that push as strong. So this is going to be a bit of a lower pressure, and it'll be like kind of just gushing back and being pushed back into the heart. We're going to see later on that over here in the capillaries, we actually have slow blood flow so that we give time for the blood to exchange its nutrients and oxygen and wastes with the cells. So we'll see that in a bit. And we'll talk about pressure later on as well. So how much blood does each blood vessel hold? The arteries and arterioles hold about 15% of the blood volume. Arteries are big, right? If you look over here, these are big vessels, so they hold a lot of blood. But at the same time, they have a big blood pressure. So they shoot the blood out quickly, and the blood just keeps moving, right? It's going and it's flowing very quickly. On the other hand, so over here, that's the arteries and arterioles. So over here, that's, you see it, all of these over here. So this is about, if you have this 13 plus in the pulmonary circuit, don't worry too much about it, but you have another like little 3% here. These arteries and arterioles will be about 15%. In the capillaries, right, we have about 5% of blood volume, approximately 5%. Here you see about 7%. But the capillaries, right, will be the smaller vessels over here. Look how tiny they are. They're minuscule. So they only have 5% blood volume, not because there's a lot of them. There is a lot of them, but they're tiny. So it's a lot of small vessels. So it's only about 5%. Whereas the veins and the venules, these are going to be bigger vessels, right? As they move away from the capillaries, bigger vessels, and also lower blood pressure, right? Remember at this point, the blood pressure goes down and it's trying to, like the hose that's dribbling the water, and also if you're in the legs and you're trying to get back up to the heart, like you're trying to get up and it's a little bit hard to go against gravity, all the blood will pool over here in these vessels, And actually, the veins and the venules, they hold about 65% of the blood volume. They act as reservoirs of for the blood. So that's going to be how much blood is in each of these vessels. And the rest is in the pulmonary circuit, right? This is the circuit going to the lungs, not the systemic circuit over here. And also the heart, right? The heart does hold some blood, only 7%, because then it shoots it out. It squeezes and shoots it out, and then it keeps on the other end. It returns some of the blood, right? So here it's going to shoot out a lot of blood, and then some of the blood will return back this way, right? Because this is called a circuit. A circuit means that it starts one way and it ends up right back where it started. So it starts in the heart and it comes right back to the heart, right? So that's how much blood is found in each of the vessels. So I want you to pause the video right now, and I want you to follow the route that blood is taken through the circulatory system. Here are your options. So read through the options, look back at the slides, and we'll compare our answers. All right, so you see in this problem here, everything starts in the heart, right? And it then goes to either, we have arteries, veins, or arterioles, right? First of all, let's go and cut one out. Once we go from the heart and we exit the heart, right? Remember, A is away. A is away. Arteries pump blood away from the heart. So you see the arteries go away from the heart. Immediately exiting the heart are always arteries, right? So it cannot be veins, right? The next one was veins here. It cannot be that. In the other two, we have arterioles or arteries, right? So arterioles sound smaller and cuter, right? Little arteries. So arterioles actually come after arteries because we have the big aorta, and that comes out the heart. That's a big artery, and then they become little arterioles, okay? So actually, this isn't quite right. Over here, we have the heart, arteries, arterioles, little vessels, capillaries, right? That's where we exchange. Venules, cute little veins, and then the big veins returning back to the heart. So this seems to be the option that I would choose. Over here, you go from arteries to veins and then capillaries. That's not true. Veins come back to the heart. They would not go back to the capillaries. Veins need to be right next to the heart because that's the next. Veins revient au cœur. So here, actually, it's heart, arteries, and then the smaller arterioles, and then the capillaries, then the venules, the veins, and the heart. So your blood vessels actually have a combination of three histological layers. Histology is the tissues, right? Three different layers. The first one, the inner layer, right? So here's your blood vessel. Inside is the blood. So here's where the blood would be, right? This inner layer is called the tunica intima. Intima sounds like internal, right? So it's the innermost layer of these blood vessels, right? So the tunica intima, the inner layer, right, contains, number one, an endothelium. Do you see these cells over here, right? These are simple squamous epithelium that are lining the lumen of all the blood vessels, okay? So they're contacting the blood. So the blood is actually going to be flowing in here, right? So this is the endothelium. It sounds a lot like epithelium. It's a special epithelium, simple squamous, just for blood vessels, okay? The lumen of the blood vessels. So here's our endothelium. Endo also means inside, right? So a simple squamous, simple squishy cells, right? Because it needs to be thin, and it contacts the blood. Under any epithelium, remember, is a basement membrane. So here you see the basement membrane in blue, the basement membrane touching the epithelium. And under that basement membrane is always a connective tissue. So here they're showing in green, this loose connective tissue in this case. Um, and then on the outside, we haven't talked about this a lot, but arteries have this little layer of elastic fibers. So here you have this internal elastic lamina. These are some elastic fibers that are most prominent in large arteries. So actually, these vessels over here, these large arteries over here, they will be the ones that mostly have this nice layer of elastic fibers. Why? Because blood pumps directly out of the heart. I want you to imagine being a little red blood cell over here and getting whacked by a tsunami wave of blood that got contracted and pushed up the vessel, right? Imagine being smacked by that wave of blood. That is a big pressure, right? Remember that here there's the highest pressure in these vessels. These vessels need to be able to stretch and expand. And if they were too rigid, right, the gush of blood might actually burst these vessels. So we want vessels that are able to expand and bounce a little bit, right? Or else there would be too much of an impact and it might burst the vessels, right? So these are often have a lot of these elastic fibers so that they can stretch a little and bounce. Okay, then so we have these elastic fibers most prominent in large arteries. Now we go to our next layer. So this was the tunica intima. Intima sounds like inside, right? Then we have the tunica media in the middle. Media, middle, right? It's the middle layer and often the thickest of the layers, right? And it contains smooth muscle. Do you see these spindle-like cells, right? These are spindle-like fibers. These will be smooth muscle that contract, right? Or relax. And remember that over here you see them very nicely. These cells, they surround. I want you to imagine them contracting and constricting the vessels, right? Making them smaller or larger. So when they contract, that's called vasoconstriction. And when they relax, that's called vasodilation. And this helps to regulate the blood pressure. So it helps to manage the different blood pressure in the artery or vein. I want you to imagine if you're a blood cell moving and you're in this little vessel, that would be a very high blood pressure. Whereas if you're in a big tube like this and you need to flow through, that would be less of a pressure, right? So actually, these smooth muscles, they help to regulate the blood pressure via the blood vessels themselves, okay? So that's the tunica media. That's the middle layer. Then we have the tunica externa. That's the external-most layer, the outermost, externa, external, outermost. So that's this layer over here, right? This layer here is made up of a lot of collagen fibers that intertwine together with other tissues around it, and it anchors the blood vessels to surrounding tissues, right? So this is where we anchor kind of the blood vessel isn't kind of wobbling in the body. It's anchored in some tissue and some connective tissue around it. That's what's going to happen over here in the tunica externa. Interesting too, I didn't talk about this, but you see little blood vessels, little tiny capillaries around here and little nerves, right? They feed the blood vessel as well. The blood vessel itself needs to have a little bit of blood supply to feed these cells over here, right? So you see them entering through this area, but not too important for our case. Let's take a look at this question. Which blood vessel tunic has the most active role in controlling blood flow? You have a few options here. Tunica intima, media, externa, or none. I will let you pause the video and take a look at these. All right. Once you're ready, unpause. The tunica intima, as it makes direct contact with blood, that doesn't control blood flow in any way, right? The tunica media, as it contains smooth muscle, which causes the vessel's diameter to change. This one makes sense. This will change blood vessel pressure, right? The blood pressure, and actually change how much blood is flowing through these vessels. Uh, so B would be my answer. Tunica externa, as it dampens the large pressure changes caused by the heartbeat. No, not really. And none, no. So I would say B is our answer for here. Now, let's go through these arteries, capillaries, veins. These are the actual vessels, right, that we will have. So we're going to start with the arteries, right? These are the ones receiving blood directly from the heart. What are some characteristics of arteries? Remember I said that arteries, they need to be very elasticy. Why do they need to be elasticy? Because they need to be have this ability to resist this very increased high blood pressure after each heartbeat. When the blood squeezes, remember I said it's one of the first vessels to receive that tsunami of blood, that big wave of blood. And if it was stiff, it might burst and rupture, right? So it needs the ability to stretch a bit as the heart is pumping. So the heart pumps and it kind of shoots out the blood, which expands a bit, and then as the heart is relaxing, the vessel also contracts back. So it has these elastic fibers allowing it for elasticity. Also contractibility, right? All the arteries have a thick tunica media, meaning it has a lot of smooth muscle, right? Remember the tunica media was all of this smooth muscle here. And what was that smooth muscle doing? It had the ability to change the diameter of the blood vessel, right? So this is actually controlled by the autonomic nervous system. The ANS is the brain regions that control things that we aren't in control of. I can't ask you right now to change your blood pressure, constrict your vessels. So it's autonomic, right? And it's the vasomotor centers in the medulla oblongata, that's a brain region in the brain stem, that largely control the arteries and the arterioles, okay? So this contractibility, this ability to change, you see over here a normal blood vessel and now it dilates or constricts, right? I want us to be comfortable with two words. Vasoconstriction, vaso means vessel, constriction means to make it smaller, constrict it. This is contraction of the arterial smooth muscle to make the vessel smaller. Vasodilation, dilating the blood vessel, is actually the relaxation of the smooth muscle, arterial smooth muscle in the tunica media, and it enlarges the vessel. It makes it bigger, okay? Types of arteries that we have. We have very big arteries. We're going to see this later on, the aorta and the pulmonary trunk. These are actually the largest types of arteries, and they come directly off of the heart, right? Remember, these big arteries, they come right off the heart, and then they go away from the heart. A is away. So elastic arteries, they're the largest type, and they have many elastic fibers. They have really this tunica intima that has a lot of this internal elastic layer, right? Again, as I said, it's to help tolerate the fluctuations in blood pressure, right? So, as I said over here, the elasticity property, it really pertains to these first vessels, these big vessels, since they're very close to the heart itself, right? So those are the elastic arteries. Then the smaller arteries are called muscular arteries. This is like maybe the carotid artery over here, right? This is an intermediate sized and kind of middle sized artery, and more common than the elastic type, because the elastic type is really just the big one that's coming off of the heart, right? And they have a very thick tunica media to help divert blood flow. Very interestingly, the muscular arteries, they're able to constrict and say, actually, don't send as much blood to this region, or dilate and say send more blood to this region. So they have a very thick tunica media. And the arterioles, these are the smallest of them, and they have a minimal tunica externa, right? So they don't have much of this external part. They're smaller, right? So they have a smaller diameter, and they are the gatekeepers into the capillary beds. They also can constrict and dilate to allow things to go into capillaries or not, right? So let's say, let me go back over here to my picture. This little arteriole here can maybe constrict and not allow as much blood to enter the capillary if it doesn't need to feed these cells as much, right? And maybe it'll go down this little arteriole and go to another capillary bed somewhere else, and that can dilate and allow more blood to go to that region instead, okay? So that's the idea behind arterioles. So these are the different types of arteries, okay? So arteries, they're carrying blood away from the heart. That's their only job pretty much, right? And they control blood pressure a little bit by constricting, dilating. The capillaries are the key job, however, of this whole system. So we go from arteries to capillaries, right? Arterioles and venules connect to capillaries, right? Remember, if I go back, I liked this picture a lot. If you go back here, right, you see that the arterioles and the venules, they connect the capillary over here. This is like the middle of the circuit, right? So the capillaries, this is where we exchange between blood and interstitial fluids. And it occurs across capillaries, right? So here's some capillaries, and you see that here probably is the arteriole, since blood is flowing in this direction. Here's the capillary itself, and here is probably the little venule exiting, right? And capillaries are the smallest vessels in this whole network, and they're almost just a single layer of endothelial cells. That's all that's there, right? It's just this simple squamous epithelium that's there. And the reason for that, why it's so thin and delicate, is because it wants to have diffusion distances as small as possible. Only one layer of little endothelial cells and a basement membrane. No tunica externa, no tunica media over here. And that makes it a lot faster, right? So it just has that tiny little distance, because the whole point of capillaries, right, is so that things can exchange across them. In the arteries, we don't want necessarily exchange. We want it just to be carried down to the capillaries, right? But here we want to exchange between tissues. Let's say, do you see these cells over here? These are tissues, and this is the blood. We want exchange between these, right? So we actually just want this very thin layer of simple squamous epithelium, right? Do you see this nice simple squamous layer, so that we easily have exchange between the two? So one layer of endothelial plus a basement membrane, no tunica externa, no tunica media, and therefore it's the fastest diffusion distances, right? Some other characteristics of these capillaries is that for greater efficiency, capillaries are organized as interconnected networks of capillary beds, right? Do you see over here how they branch like this? I really like this picture. I should have put it over here. You see that this arteriole, it branches into many branches, right? That's because in our toes, right, we might have a little cell here to feed. We might have a little cell here to feed, a little cell over here. So it's actually good that it could branch out, because it could feed all of these cells that are in the toe, right, very far away, and it could exchange with a big, vast area of that tissue. So that's why we have, for greater efficiency, they're organized into interconnected networks of capillary beds. You have some capillary beds in your toes, some in your legs, some in your trunk, some in your head, right? Because you need to feed all of those tissues. So there's many capillary beds everywhere, right? So microscopic capillary networks permeate all active tissue. Every single tissue cell in the body, every tissue, every cell needs access to the blood network, right? And so capillaries go in every active tissue except in epithelium and cartilage. But remember, near epithelium and cartilage is always a connective tissue under. So in the connective tissue, there's capillaries and they diffuse away that oxygen and glucose into the epithelium. So it's not that far from the epithelium, right? It's just that it's a little bit below. Same thing for cartilage, okay? But every active tissue, it's true that every active tissue needs access to, I could put it that way, to a capillary network. Either it be directly next to it or just a little bit below in the connective tissue, right? That's important. Because if cells don't get oxygen and their nutrients and they can't get rid of their waste, they don't make ATP. They die, right? And they necrose, they go black, and they will die and crust, right? So that's, we need to feed those tissues. Some characteristics of capillaries. Again, I want to emphasize they are the smallest of the vessels. They are tiny, tiny little vessels, similar in size to a single red blood cell. You can't even see a single red blood cell. So imagine how small these are, right? We have vessels like the arteries that we see big vessels, right? But these are tiny, microscopic, similar in size to a single red blood cell, because it's kind of nice that these capillaries actually will put one single red blood cell in line after another flowing through these so that it maximizes the exchange between the tissue and the blood vessel itself, right? So that's quite nice. Let's examine various capillary beds, right? Well, first of all, we have the pulmonary capillary beds, which will go and pick up oxygen to bring back oxygen to the heart. It'll help to oxygenate your blood. So the heart sends, let's see over here, we see that it sends these blue deoxygenated vessels to the lungs. It goes to the lungs here, the pulmonary beds, the pulmonary capillaries. It picks up oxygen and it returns as red. You see this red over here? It comes back. Here it sends, it also sends it to this side, goes to this lung in blue, reoxygenates and comes back as red and enters back in this way, okay? The systemic pulmonary beds perform various functions in different areas. Some of them vascularize the upper body or the lower body, right? So there's some capillary beds in your head. There's some in your arms, in your legs, right? And some of them vascularize the abdominal pelvic organs. We call these the enteric beds. Enteric system is like the gastrointestinal system. So over here, do you see all these capillaries that are going to like the stomach and intestines here? They feed the intestines, which also feed the portal system in the liver. So there's a whole system going on here of capillary beds. And what is it that happens at the capillary beds? We kind of went through this already, but materials are exchanged between the intravascular space and the interstitial fluid. So I'm going to draw over here. I want you to imagine that this is a capillary bed and that there's these toe cells over here, right? These little cells that we need to feed. They are needing glucose and oxygen, right? Well, what's going to happen is I'm going to take a zoom of this here, right? And actually I'm going to put this space here, I'm going to put it in purple. Pretend this is all purple space because that's the interstitial space. What happens at the capillaries, as I've said before, is that materials exchange between the intervascular space inside the blood vessel and they exchange into the interstitial fluid, and then they go into the intracellular space, right? So let's say something like oxygen or glucose, which the cells need. They will go from the intravascular space, they will enter into the interstitial space, which is full of fluid, interstitial fluid, right? There's some fluid over here between the cells. and they will then diffuse into the oxygen, and glucose will diffuse into the intracellular space. It'll go into these cells, right? So that is the where we're going to go. And then once we've exchanged there, well, we're going to go back into the all the waste, the CO2 and the metabolic waste will go from the cells to the interstitial space, back into the vessels. And now we have this blood that's deoxygenated without any more glucose, right? We've given away all our glucose and we return back to the heart. So, what do these capillaries allow us to do? They permit exchange of water. We can exchange water, small solutes, and lipid-soluble material. But at the same time, they retain blood cells and plasma proteins that are too big, right? These red blood cells never leave into the cells over here or the interstitial space. These red blood cells are way, way, way too big. So it's actually just the oxygen in these red blood cells on the hemoglobin that will cross into this space and exit. Remember that the hemoglobin can unbind the oxygen and let it go. So never will you see these red blood cells enter here. That's not good. Actually, if that happens, you get bruising. That's what bruising is. It's when little vessels, little capillaries burst, and they allow the red blood cells to enter into the interstitial space, giving it a bruised color until it gets like filtered out by the lymphatic system. So that's going to be, we actually want to retain under normal circumstances the red blood cells here and the plasma proteins. Remember albumin, remember the globulins, remember fibrinogen. All of that should stay over here in the vessel, right? So these big albumin molecules, right, they will stay in here because they don't fit through these little slits here, okay? So that was for the capillaries. So now we saw arteries are vessels that bring blood to tissues. At the tissues, we have capillaries, which are small vessels that allow exchange. And now we're going to talk about veins. And veins, there are different types of veins, just like there were different types of arteries, right? Unlike arteries, veins generally have much thinner walls. They're very, very thin compared to the arteries. Why are they thinner? Remember what I said about blood pressure, right? At the beginning of the hose, the garden hose, if you're a blood vessel and you see the tap of water opening, it's going to hit you like a wave. The pressure is huge. You need to be able to have this elasticity and a thicker wall to make up for that big wave of the tsunami. At the end of the garden hose, remember that water just dribbles out. The pressure is low. So you don't even need a big wall. Veins don't have a large pressure in them. So they don't need to make sure that they don't burst, right? The pressure is a lot smaller. That's why they're thinner. So veins generally have a much thinner wall, and they're classified based on their internal diameter rather than their wall composition, okay? So venules, right, they're the smallest type, and they're very small, and they're right after the capillaries, right? If we can do our circuits, we had the elastic arteries, we had the muscular arteries, we had the arterioles, we had the capillaries, and then it's the venules, the smallest type, right? They have no tunica media, they're not contracting, and they collect blood from the capillary beds. The medium veins, they have a thin tunica media, but a very thick tunica externa here. The medium-sized veins actually have a role in thermal regulation as they occur closer to the surface of the skin. This little tunica media can constrict or dilate and send more blood towards the skin or less blood. So, you know, when you go for a run and you start getting very red on your face, let's say, that's because those little medium veins will open up and allow more blood to go to the surface of the skin to try to expel heat. Or the opposite is true, right? When we become very cold, right, these will try to constrict and not send it to our surface of our skin, And that's why we get a bit pale, right? When we're cold, because that blood is trying to be conserved inside the body, and those medium veins will stop a lot of blood from going to the surface of the skin to keep it inside and keep our heat inside and thermoregulate. The large veins, right? Those are the ones that the last in the circuit, right? So even less of a pressure inside. The large veins are returning back to the heart. And those that are coming back to the heart, we're going to see later on, is called the vena cava. And the pulmonary veins, they're coming back into the heart. They're very big vessels. They have a thick tunica externa made of collagen and elastic fibers to withstand the high amount of blood volume, right? Because they're the reservoirs. They actually hold a lot of blood. They're a bit floppy too. We're going to see that in a minute. So what are some characteristics of veins in general? Large veins commonly run alongside the arteries back towards the heart, right? So an artery will be going downwards, going to the capillary, and then the vein will come back along the side of the artery. They'll be kind of stuck to each other, but not connected, right? But they'll run together parallel almost, but in different directions from the heart. So veins have, again, I keep repeating this, veins have a low blood pressure, right? Since they are the furthest away from the heart and they're only partially filled up, right? Because they're the reservoirs also, so they have very low blood pressure. The low blood pressure in the veins means that they require valves, little folds in the endothelium, little folds over here. These are called valves in the tunica intima to prevent backflow against gravity, right? Because remember, the heart makes a pressure, it keeps beating and sending blood around, but at the end of the hose, it's kind of going back up slowly, right? And imagine if there weren't these valves. Let's say the heart is up here, right? And we're trying to go against gravity from the legs all the way back to the heart. Imagine if these little valves weren't here and there was a push of the heart, a squeeze, and the pressure goes up. It doesn't make it all the way back to the heart. And imagine these valves weren't there, it would go all the way back down to our feet. And actually, people with varicose veins, like that are in their feet and you see their veins, that's maybe due to a pressure problem where the blood is not going up to the heart properly and it's accumulating in those veins at the bottom, right? So actually, these valves are important to prevent backflow against gravity as the heart is relaxing and not giving a push, right? The blood will actually stay in this little valve and then the next push will push it through to the next little valve and on and on and on, right? So it helps to prevent the backflow of blood against the gravity. And actually, blood moves up the veins against gravity, right? And one of the things that help us do that are the what we call the skeletal muscle pumps. So blood moves up our veins, right? It needs to go back to the heart, so it moves against gravity. And as the skeletal muscles contract, as you're walking, right? This is the gastrocnemius muscle. As you're walking, this muscle will contract, right? And relax. And there's this big vein over here that's going right back up to the heart. And so as you're walking, this will contract and relax. And here, for instance, when it's relaxed and your foot is flat, you see that the valves will close over here. And as you lift your foot up, right, this squeezes over here and actually forces the blood to push back up. So in a sense, the skeletal muscle is almost acting as a heart, right, to create a pressure to allow for your blood to go up to your heart. It's not the main reason why blood flows, but it does help to mechanically distort the vein and squeeze the vein so that blood does go in the proper direction, right? So valves are pushed open and they'll prevent backflow to allow for blood to move towards the heart. So valves open, right, when you're going to contract this muscle and you're allowing for the blood to go. And then when your valves that are below the muscle will actually close so that you're not going to backflow it down, right? So all this to say, the skeletal muscle does help to create a little bit of a pressure. This is called the skeletal muscle pump. That does give a bit of help. And this is why, some people wear compression socks, let's say, right? Because it creates this little pressure here that does help with blood circulation. Or why they say to, walking around and just moving does help with circulation and activity. Physical activity does help because you're moving your muscles, you're helping to move the blood around. So that's pretty much what we have here. What is the difference between systemic arteries and veins? So the arteries and veins have some differences, right? So the arteries, this is artery again, this is histology, this is tissues. I want you to imagine these cylinders, right, of arteries and veins that got cut into two. So you're looking down at the 2D image of that, right? That's what tissue histology looks at. So you're looking at this is your artery, the round artery. This is the middle of the artery where the blood flows, and this is a vein, and this is where the blood flows in the vein. You notice that they look different, right? The arteries are smaller and they're more circular. They're lumen, where the lumière could be shone through, right? Where you could look at where the blood is going. That's the empty hollow part of a tube. The lumen of the artery is more circular, right? That's because they have and you notice over here, look at this big thick layer of something, right? This is actually a thick layer of tunica media, more smooth muscle that's found in that tunica media compared to here. Look at the tunica media here. There's almost nothing, right? Here we have a very thick tunica media. Here we have a very thin tunica media, smooth muscle. Because in arteries, remember that we need to be able to vasoconstrict and vasodilate, right? We need to be able to expand because of what? Because they need to be able to change their shape to regulate the blood pressure, right? They're able to go and change this how much blood is flowing to a certain region or not, and that can change the blood pressure of this whole system. Additionally, in arteries, you also see an extensive tunica intima appearing wavy, right? You have your endothelium here, and do you see all these little wavies here? That's called the internal elastic membrane. It's wavy due to the elastic layer. We have this wavy, you don't see it very much in this picture. It would be kind of inside over here somewhere. You don't see this wavy layer here in the tunica intima, and you don't see these little wavies inside, right? Because in arteries, we need elastic fibers, especially the bigger arteries, like the elastic ones, because you're right next to the heart, and when the heart pumps, you get that wave of blood, and it needs to be able to recoil. If it was too stiff, like a vein, that high pressure would burst it because it would not be able to withstand that wave, right? So those are arteries. Veins, do you see how they're much larger? And that makes sense because remember in the slide of blood volume, I said most of the volume of blood is actually found in veins. They're the reservoirs of all of the circuit. They collect excess blood and they really hold a lot of blood. Also because it's harder to carry blood back to the heart and it takes longer due to the pressure differences. So that's why we have these larger veins. They're distended and they're floppy. Their lumen is floppier. They have this thinner tunica media. Look here, very small. You don't see a very large compared to here tunica media. And it has a smoother looking tunica intima. There's not as much elastic fibers. Remember, the pressure is very low in the veins, so it does not need to be able to recoil back and recoil and stretch because there's not big fluctuations in pressure from the heart. We're at the end of the garden hose for the veins, so the pressure is low, right? So here's a little summary of what we just talked about. It's a comparison table, the difference between arteries and veins. Arteries carry blood away from the heart, veins carry blood towards the heart, right? Arteries carry oxygenated blood, except for pulmonary arteries that we'll see. So usually in the systemic circuit, right, we are always bringing blood that is oxygenated to feed the cells, but actually in the pulmonary arteries, there's an exception. You're going to the lungs to go and get oxygen. We're going to see that in a bit. Most veins carry deoxygenated blood except for pulmonary veins. We're going to see that most veins are coming back to the heart, revient au cœur, so that they can they can send back that deoxygenated bad blood to the heart, except for pulmonary veins. When the pulmonary veins are coming back to the heart, they're actually coming back oxygenated because they picked up oxygen from the lungs. Usually these are brighter red. These are usually a darker red or purple. That's based on them carrying oxygen and how the iron reacts with the oxygen, if it's bound or not. Arteries have a thick wall and contain a higher proportion of muscle, this smooth muscle layer, huge, and elastin, right? We just talked about why that is, because it needs to be able to constrict and dilate, and also because the elastic fibers help resist big pressures, right? Here we have a thin wall, right? And it contains a lot less muscle and elastin because it's low pressure that we don't need to really worry about too much. They have many internal and external elastic laminae, so the arteries need to be able to withstand that big pressure. Here we don't have much elasticity. A narrow lumen, right? Very small lumen because blood is it's being sent quickly away. Whereas veins have a much bigger lumen. They are the reservoirs in a way. It does not have valves, the arteries. It's not needed because the pressure is so high that it's just going. Whereas the veins, they do have valves to prevent backflow because sometimes they're going against gravity, which they need to prevent it from going back down to the legs. And the pressure is a lot slower, right? So sometimes it doesn't get all the way back up to the heart, so it stops at a pit stop. It goes up a bit, it stops at a vein, and then at a valve, and then it goes back up, and it could reach the heart. So it does like a pit stop halfway up to the body. And then lastly, and probably most importantly, but we're going to go through this more at length in a bit, the arteries have a higher blood pressure because they receive blood directly from the heart, whereas the veins have a lower blood pressure. They deliver blood back to the heart, right? So these are right at the beginning of the tap, right next to the heart. So they receive the big tsunami wave, right? But further away, that wave propagates, yes, but as you get further away from the heart, the source of the tsunami, the waves get weaker, right? So in the veins, there's a lower blood pressure to deliver blood back to the heart because you're further away from the source of the wave, which was really the arteries that received that. So the key thing here, arteries resist the large fluctuations in blood pressure, and they could divert blood flow with their because they have that muscle layer. They can divert blood flow from in one direction or another. Veins, they withstand a greater blood volume, right? They have a lot more blood inside of them. So they have this thicker externa, and valves help to prevent backflow. Do you see this little valve here, right? You see that this is the valve. Blood will go up, it'll push against it, and let's say it pops. It doesn't reach all the way up, but then it'll fall back, and at least it won't go all the way back down, right? It'll just stop here, and then the next pumping of the heart will cause it to go a little bit further, and it might get back to the heart after that next pump. All right, so over here, the question asks, which of the following statements regarding arteries and veins is true? Let's go, so pause the video and try to attempt it on your own. When you're ready, you could unpause. We're gonna go and look at each of the options. So here, arteries have less smooth muscle than veins. Is this true? Actually, the arteries have more smooth muscle, right? Because remember, they're the ones that are really able to vasoconstrict and vasodilate where the blood is going to go to exchange, right? So actually, I'm going to say no to this. Arteries have more smooth muscle. Arteries always carry oxygenated blood, while veins always carry deoxygenated blood. For the systemic circuit, it's true, going to tissues, but actually in the lungs, it's not true. And we're going to see this more in detail soon, but I do want to emphasize that arteries going, the thing that really defines an artery is whether it's going away from the heart or not whether it's oxygenated or deoxygenated, because there's an exception in the lungs. At any given time, there is more blood in the veins than in the arteries. This is very true. The veins are the ones that contain a lot more blood. They're the reservoirs of blood, okay? And there tends to be a lower pressure in the arteries than the veins. This isn't true. The arteries are the ones going away from the heart, so they're the closest to that contraction, right? They're the closest to that tap of water, right? So they're the ones with the highest pressure, actually. So arteries have high pressure compared to veins, which are at the end of the circuit. So the correct answer is C here, okay? Alrighty, so we'll erase this. Let's put that. So over here, let's take a look at some things on hemodynamics. What are hemodynamics? Hemo means blood, and dynamics means that it's moving, right? So it's the physical principles of blood circulation. How does it circulate, right? How does it get around? There's certain measures, physical measures of how blood is moving. Dynamic means to be able to move, right? It's not static, it's not still, it's moving, it's dynamic. So what are the three measures of hemodynamics? The first one is called blood flow. Blood flow is the volume of blood flowing through a particular point in a given period of time. And so you could think of a unit like milliliters per minute, right? How many milliliters, if you were, like, I like to think of a speedometer, like on the side of the road, measuring the speed of cars, right? If you had a speedometer and you were measuring the amount of blood going by in a minute, what would that blood flow be, right? Kind of like the speed of the blood, right? So here, the blood is saying, let's speed up. Blood flow is only 5 mils per minute. So then they start speeding up and going 20 mils per minute, right? And they're going to go faster through the vessel. So it's really, this is more of the amount of volume per minute. Any flow, any speed, right, is always measured by the kind of the amount, right, that's going per minute per a specific period of time, right? So this is mils per minute. Blood pressure, right, is a bit different. It's the force that blood exerts on the walls of the vessel. So if you think of a tube, right, and you have a lot of liquid in it, the blood will be pushing on the tube, right? Think of, like I said, like the tsunami wave entering into that big artery. It pushes on the wall and actually makes it expand thanks to the elasticity, right? It could move. So it pushes on the walls of the arteries. So blood pressure is how much a pressure is. You could have a small pressure if someone just pokes your cheek, or if they punch you, then that's a big pressure, right? So it's a force exerted on the vessels, the wall vessels, right? And this is actually measured in millimeters mercury. This is a unit to measure pressure. Resistance is any opposition to blood flow. So it measures the amount of friction that blood encounters, right? There's always resistance to going forward in a blood vessel. Here there's low resistance. So here these little red blood cells, they're just moving through as a breeze in the blood vessel. And then all of a sudden, if I squeeze the tube, right, and make it smaller, then I've just increased the resistance, and it makes it a bit tougher for this blood to flow through, right? So resistance is the countering of it. Or imagine if I blocked the vessel, right? And I put a big clump of fat on the side here and narrowed the tube because of this plaque that accumulated, then the blood wouldn't be able to move as fast in the vessel. So I want you to pause the video here, and we're going to look at this question. Which of the following is an appropriate analogy for increasing resistance to blood flow in the blood vessel? So I'll let you pause the video and take a look at these answers. Okay, so option 1, lubricating a garden hose so that water can flow through it faster. Well, remember, resistance is the countering force. If you increase resistance, you make things harder to flow through, right? Increased resistance means that it's harder to get to. So lubricating a garden hose and making the water flow faster, that's actually a decrease in resistance that would allow the blood to go faster, right? So it can't be this one. Let's go X this out. Cutting the end of the garden hose so that the water has a shorter distance to travel, right? That's not really affecting our resistance per se, right? It's just making the whole circuit a bit smaller. Cutting a hole in the side of the garden hose so that some of the water leaks out as it flows through, right? So this would just deviate the path of the blood out towards a different area, right? So I wouldn't say that. And then squeezing a garden hose, thereby slowing down the water flow through it. If I constrict the vessel and make it harder for the blood to go through, then that's the idea of resistance, right? You're increasing and making it more difficult for the blood to flow, right? Okay. Good. So we're going to go through each of these hemodynamic measures one by one. So flow, pressure, and then resistance. So blood flow, right? If I talk about blood flow, this is the volume of blood flowing through a particular point in a given period of time. So it's the milliliters per minute. The mils, how much blood per minute that is flowing, right? And so this has to do with, we don't use necessarily the term blood flow in clinic. We actually use the term cardiac output and exchange rates to speak about this. So cardiac output is what we measure as for blood flow. It's the volume of blood that's pumped by the heart every minute. So in 1 minute, how much, if you took a little cup, right, and you put it right under the artery, the big artery that's coming out, and you collected all of that blood in 1 minute, that would give you a certain amount of milliliters in that 1 minute, right? You would measure how many milliliters it is, and that is what cardiac output is. It's the output from the heart, from the cardiac, right? So that's the volume of blood pumped by the heart every minute. This is a measure of flow. You're measuring how much is exiting, right? And so this is a measure of blood flow, but you could change blood flow in 2 ways, okay? You could change blood flow if you increase the stroke volume, okay? So the stroke volume, a stroke, right, is like one contraction. So 1 beat, right? The volume of 1 stroke is what we're talking about. Like a stroke, think of like in a kayak, 1 stroke would be to paddle and advance once, right? That's a stroke of your paddle. So this is the volume of blood that's ejected by the ventricles in just for 1 beat. So think of the heart, right? And I want you to think of a straw coming out. Pretend that's the artery. If you take the water balloon and slightly squeezed it, right? A little bit of water would come out. A little bit of blood would come out the heart. If you took the water balloon and squeezed it hard once, a lot of water will come out, right? So that stroke volume is how much is coming out in one beat only, not many beats, one beat. So this stroke volume, right, will influence the cardiac output, because if you're squeezing hard or not hard, that will increase or decrease the volume of blood that's pumped out every minute. And the second measure that's important is the heart rate, the number of heartbeats in 1 minute. So the heart rate can change in beats per minute. So I'm not talking about strength. Remember my water balloon? I said you could squeeze it strong or weakly. That's stroke volume. Now what I'm talking about, if you keep the same strength, a medium strength, right, that it's pumping at the same strength, you could change the speed that you're pumping at. The same force, right? The same force, but you could start beating a bit faster, right? Or slower, right? That's the heart rate, how much that heart is actually going to be pumping, the number of beats per 1 minute. So this is stroke volume changes the rate. Stroke volume is changing the volume that is coming out in one beat, right? So that's the strength of the heart. And heart rate changes the speed of pumping, right? So I like to think of, transferring water from one bucket to another. If you had a cup, right? If you had a small cup and you were taking water and putting it into the other bucket, and you had to keep transferring that water, and all of a sudden you were giving a huge bucket and you were able to get a much bigger amount to transfer, that's changing the stroke volume. That's changing how much blood will be ejected every scoop. Versus if I had a 1 cup, right, and I started to put the water and start transferring it, but then I sped up my speed, right? Like then I was going faster to transfer back and forth, then that's changing the rate, the heart rate, right? So that's the idea of flow. Flow could be affected by the strength of contraction of the heart or by how fast the heart is going. Both of them would influence your flow, your cardiac output. So cardiac output is the blood flow through the body. It represents the total volume of blood that's pumped by the heart, and it influences capillary exchange. Why does that influence capillary exchange? Because if blood flow is too fast, there would be inadequate perfusion, right? Which means that there's not enough time for exchange, insufficient exchange time for gases, nutrients, and wastes. Imagine if at the capillaries blood is going fast, they wouldn't be able to exchange oxygen and glucose and all of that stuff. The opposite is true. If it's too slow, the blood won't be carrying enough of that stuff to the capillaries, right? And it'll be too slow to provide the nutrients and the oxygen. So perfusion, right, means to perfuse a tissue means to send stuff to the tissues, right? So we want blood to perfuse the tissues adequately at the right speed. So we want a proper cardiac output to be sending blood to these regions at the right speed. Now, blood flow, remember, I'm leaving the definition here. It's the volume of blood through a particular point in a given period of time, right? So I want you to understand that blood flow, remember I told you about the 3 measures, flow, pressure, and resistance. Flow, they're not all separate, right? Flow is actually directly driven by the pressure gradient, delta P, and it's also affected by resistance. So the blood flow, I know this looks mathy, but don't worry about it. The blood flow is directly proportional, that it's equal to the pressure that's in the vessels, divided by the resistance, okay? Let me make this simple, okay? Blood pressure, right, this delta P here, is influenced by the force at which the blood is pushed out of the heart. So this is like a change, let's say, in the stroke volume, right? Let's say the heart contracts a lot stronger, then blood pressure is proportional to the blood flow. And so you're going to increase the pressure, and this would also increase the blood flow, right? So the pressure in the vessels, actually, where does the pressure in the vessels come from? It's not the vessels that are contracting, it's the heart that contracts, right? So delta P, the blood pressure, that all comes from the heart that's contracting and squeezing. So if you change the stroke volume, you change the pressure. If there's a stronger pressure, then there'll be a stronger flow, right? If the heart squeezes stronger, like the water balloon, I squeeze the water balloon stronger, more water will exit the straw, right? And over here, so these are, we call it directly proportional, because if you increase pressure, you increase flow, right? If flow increases, that means the pressure increases, right? So that's blood pressure. Resistance, on the other hand, is any opposition to the movement of blood. So actually, I'm going to draw it here. The pressure, okay, delta P, this delta P here, is generated. Here's the heart, okay, that squeezed and generated a pressure in this direction, right? This is like my delta P, okay, my change in pressure thanks to my heart. Resistance, on the other hand, okay, is any opposition to the movement of blood. So resistance is actually going to be, this is what resistance is: anything that stops the blood from moving in this direction, right? So this depends on the vessel length and diameter. If it's smaller, then it's harder to go through, whereas if it's bigger, it's easier for the blood to flow through. We'll see that it depends on the blood viscosity. Let's say your blood is thicker, like honey. It's harder to push honey through a tube than it is to push water through a tube, right? Think of squeezing out honey out of a container versus water, and you turn them, it's a lot easier for water to go through, less friction, less resistance, right? And also obstruction. Let's say I had a clot over here that made the vessel obstructed, then it's harder for the blood to pass through. So that's part of resistance too. This is all a piece of peripheral resistance, right? Any resistance in the peripheral blood vessels, right, is going to be countering the flow. So do you see how resistance is on the denominator, right? It's called inversely proportional. It's not on the numerator, it's inverse to that, right? Because if you increase the resistance, you're going to be decreasing the flow. If you put more obstacles in the blood vessel or make it harder, like smaller or more viscous, you're increasing the resistance. That will make things slower. The flow is slower. That's why it's inverse, right? If you increase this, it's the inverse. It decreases flow. If you decrease resistance, right? Let's say your blood vessel gets bigger, right? Well, now a lot more can flow through. So if you decrease resistance, you actually increase your blood flow, right? So they're inverse. That's, I think, the point that I want to make. And I know this is mathematical. If you don't like math, don't listen to this. But if my pressure increased, right? Let's say this used to be, I don't know. Let's say the pressure was 20 and the resistance was 10. I'm making this up, right? 20 divided by 10, right? Over here you have 2, right? So if for some reason my pressure went up, right? If I increase my pressure, meaning my heart contracted faster, my stroke volume increased, and my pressure went up to 100, right? I increase my pressure. What happens to my flow? This is 100 divided by 10. This is going to be 10, right? I'm going to go from 2 and I'm going to have 10 now, right? That's an increase in flow. My pressure increases, my flow increases, okay? Now we're going to go back and we're going to put our numbers back. Remember, this was 20 and this was 10, right? And this was 2. If all of a sudden my resistance went up, right? Let's say that this over here, right, went up to 20, let's say, right? All of a sudden, I have 20 units of this resistance, 20 divided by 20, right? So I increased my resistance, meaning something was preventing the flow. So 20 divided by 20 is actually, now it's going to be 1. Do you see that my flow decreased? So if I increase resistance, this is a bigger denominator. I'm going to divide by a bigger number and this flow will decrease, right? So now I'm all of a sudden at 1. If math is not your thing, then don't worry about it. But if it makes sense to look at this formula, then go for it. Use that as a helpful tool. Okay. So that was flow. Now we're going to talk about pressure, okay? So for pressure, I want you to remember what pressure is. It's the force that blood exerts on the walls of the vessel. Do you see over here when the heart pumps? Do you see how there's a little bulge in the vessel, right? That's a pressure against the walls. As I said with the water balloon and the straw in it, or the juice box and the straw, if you squeeze that water balloon like the heart does here, right, that will create a pressure that pushes the blood along. That's a pressure along against the walls that pushes the blood along, right? And that's what allows blood to move, right? It's this blood pressure. And I told you that we actually measure blood pressure in millimeters mercury. You don't need to know the details of this, but the unit comes from actually the amount of millimeters of mercury that the atmosphere is pushing onto mercury. So if we just put a tube of this glass of mercury, right, at rest, the atmosphere pushes down onto this mercury and lifts it up in the tube at 760 millimeters. Okay, so there's 760 millimeters of mercury for the atmospheric pressure. But in the blood pressure, you might measure more or less of a unit based on what the blood pressure is. So you don't need to understand this too much, but if it helps to understand that, oh, this is a pressure of the, mercury is measuring how much of a air pressure is pushing on it, well, then this might help. But if you don't really get all of this, don't worry. So in other words, pressure is a force over a specific area, right? I want you to imagine this is like the lumen of the blood vessel, right? There's a certain force from the heart contracting, from you squeezing the water balloon, that causes the blood to move over a certain area, right? And that force divided by the area is the pressure, okay? So, all this to say, right, the blood flow, this is the flow, right? It is, and the circulatory pressure, right, must overcome the total peripheral resistance. So actually, I'm going to go back to, I think I had a picture over here. I told you about the fact that there's this pressure over here, right? Delta P. I told you that there's this resistance over here, right? Like, let's say this much. If my resistance is too strong, then, and it's the same length as the pressure arrow, then my blood stops moving, which isn't the case. It never happens, right? But over here, you see the resistance is counteracting this force. So the net force, or the flow, right, is actually the addition of the pressure minus the resistance, right? Like we're looking at the fact that the net flow is based on what the pressure is, and if you remove whatever is resisting it, that's what you're going to get as a net flow of your blood. So over here, same situation that you see for blood flow, the circulatory pressure, the pressure in the tubes, must overcome the resistance, right? Here you see that the resistance is maybe going to be pushing, wrong direction. The resistance is going to be pushing in, let's say, this direction, right? Since blood is flowing this way, your resistance is going to be pushing this way. The pressure, right, must be pushing in this direction because that's where blood is flowing. That's what's creating the blood flow, right? So here you have the blood flowing this way, right? The pressure is pushing this way, and the pressure must overcome this resistance of the walls, of the viscosity. So that's what blood pressure is. It's and do you see how we saw this delta P, this change in pressure? Because the pressure over here, right, which is right next to the heart just contracted and had a very high pressure over here, right? And then as it goes down at this end over here, let's say, or P2, the pressure decreases. I want you to understand something. The pressure, if you're a little blood cell right here sitting and smiling, you will feel the wave of the tsunami very hard, right? Poof, it'll hit you. But if you're actually over here, right, that tsunami wave, you're a bit further away from it and the wave won't hit you as hard as it did over here. So the further away in the vessel you are, the more the pressure goes down. I told you about this. In the arteries, it's very high. In the arterioles, it's medium. In the capillaries, medium. In the venules, lower. And in the veins, very low, right? So the pressure closer to the heart is very big, right? And the pressure as you go down the vessel, right, it's a smaller pressure. That's why the delta P is what's important, because it's the change in pressure that makes things move. Here there's a high pressure, here there's a low pressure. So this high pressure will want to go towards the area of lower pressure. That's why this blood is flowing, right? So I want us to think about the average blood pressures of the systemic loop. The first thing to note, right, is that the pressure in the heart, right, this would be the pressure in the heart. It's the highest during ventricular systole. Ventricular systole just means contraction of the heart. So when we contract the heart, right, this is the highest level. So it's actually going to be at 120, the pressure. So if we look over here, it'll be actually at 120. And the lowest end, so the heart contracts, the pressure of the blood is 120. And when it relaxes, it's going to be 80. It'll be here. So actually the pressure in this part of the heart, it fluctuates up like this. And here I just put the average. I put the average as 100. Because if you do the average of 120 and 80, it gives you 100. All this to say, right, you've maybe heard of the number 120 over 80, right, for blood pressure, because that's the pressure that's in the arteries from the heart, right? 120 over 80, 120 over 80. When you measure blood pressure, you put a cuff here and you probably are measuring the artery that goes to that area, to the hand, and it's very close to the heart, right? It's somewhat close to the heart. So you're measuring 120 over 80. It's contracting and relaxing, contracting, relaxing. So that's what you see in the heart. In the arterial pressure, right, blood pressure is the highest in the aorta. So the first vessel coming out of the heart that receives the tsunami wave of the contraction of the blood, right, that receives that blood entering it, that's the highest. It's at 100 millimeters mercury on average, because it's between 180 and 120 and 80, right? Remember I said that's an average. And the lowest in the arterioles, right, if I go down, is around 35 over here. That's close to the capillary beds. The arterial pressure, average pressure is about 35. Remember, as I go down my system, down my garden hose, at the very end, it is the lowest pressure. It's highest near the tap, and it's lowest at the very end, and it just slowly goes down in pressure along the whole hose. So that's why this curve looks like this, because the elastic arteries have the highest pressure, and then they flow down to the muscular arteries. They have a pressure, and then down to the arterioles, we're down to 35 millimeters of mercury, right? This is a measure of pressure, by the way, millimeters mercury. Remember that. Then we're going to have, so we have this 35 millimeters mercury, and then we have the capillary pressure, or they call it the capillary hydrostatic pressure. This occurs across the capillary bed, okay? So think of the capillaries where there's exchange with the other cells. The blood pressure there is highest at the arterial end. Near the arterioles, it's at 35, as I said. And at the venual end down here, it's at around 18 millimeters of mercury, okay? And lastly, the venous pressure in the veins decreases from about 18 at the venual end, just this is over here, right? About 18 at the venules. Then it goes through the veins, right? And then the vena cava right next to the heart. And it becomes about just 2 millimeters mercury at the vena cava, right? This is called central venous pressure. Returning to the heart is like 2 millimeters mercury. It's nothing. The pressure is so low because remember, here I'm right next to the heart that just sent a wave of blood, right? And as I go down the garden hose, that pressure just goes down, 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 down till I get back to the heart. Once the blood is back in the heart squeezes it and shoves it back out into the arteries, and then it goes back in the system and comes back to the heart, right? So that was flow, that was pressure. Now we're on to resistance. Resistance is any opposition to blood flow. It measures the amount of friction that the blood encounters. And there are 4 ways to have friction in a blood vessel. Number 1, the blood vessel length. This one's not as important for us because we're talking about circuits. We're talking about circuits that are all connected, so it's not as important. But the longer the vessel is, the greater the resistance. Think of it this way. If I have a short hose that's attached to the tap, right? The garden hose that's attached to the tap, and I turn the tap on. At the very end, this will have a long, this will be a short vessel. So the high pressure here will be just a little bit less high over here, but it'll still be strong, right? Whereas if I have a longer vessel, a longer hose that's meters long, right? Here's the tap. Over here, it's going to be very high pressure, very, very high. And then it's slowly going to slow down. As I get to the end here, it'll be very low pressure. So the longer the vessel, the greater the resistance, right? Let me write it over here. Here I have a short vessel, right? My resistance is very low because I have a shorter distance to travel. The molecules won't lose their energy as they get to the end. Here I have a long vessel, so all these molecules of blood will be bouncing around, and by the time I get to the end, they lose a bit of that energy, and the resistance is going to be very high, and it's just going to leak. The water, right, is just going to leak out over here and be bleh, right? Whereas here, the water will like spurt out because the resistance is so low, the vessel is so short. This is, it's not as important as I said in our case because we have a full closed circuit. The ones that are important is blood viscosity. The more viscous that our blood is, the more resistance that it has. What does viscosity means? It means thick. Honey is more viscous than blood, right? So it actually creates resistance due to friction between the formed elements, right? Like the blood cells and or the plasma content, right? Like the plasma proteins. So think of it this way. If I have thicker blood, more formed elements and plasma proteins, more red blood cells, more white blood cells, if I have a lot more of it, right, then the blood will be thicker, right? Because it's less watery. Think of a soup, right? If you have a soup with like 4 vegetables in it and the rest of it's water, it's a very watery soup, right? It's going to be low viscosity. If you have a soup with mostly like big chunky vegetables, then it's going to be more viscous, right? I want you to think about maybe shooting that out of a syringe, right? Imagine you put water in a syringe or honey and you try to push the water out. That would work very well for water. You would have low viscosity and low resistance because the water would shoot out quickly. It easily passes through, it's not thick. If you put honey or blood with more cells in it, right, or more plasma proteins in it, it becomes thicker. I want you now to think of putting honey in a syringe and you shoot it out. It'll be slower and you'll have to push harder to exit the honey. That's because there's a higher resistance, right? So the hematocrit, right? This is a measure of the percent of red blood cells in the blood. So a hematocrit is you take the total amount of blood, right? And you take the amount of red blood cells. Remember, this is the amount of erythrocytes, right? And if you take the number of erythrocytes and divide it by the total, so here I have 45 for the red blood cells divided by 100, then my hematocrit is 45% times 100, 45%, right? This is a normal hematocrit, about 45%. It measures the amount of red blood cells, this value. Here, for polycythemia, this is a patient that has 70 units over here divided by 100, my total amount of blood. 70 divided by 100 times 100 is 70%. 70% of my blood is red blood cells. That's going to be a chunky soup, thick, a lot of vegetables in that soup, right? It's going to be thicker. This is more like honey. This is more like watery, right? So the viscosity of the blood can change, right? And actually, this is called polycythemia. Poly means too many, right? Many, and then cythemia, too many cells, right? And so this is a condition where there's too many red blood cells, an increased number of red blood cells, which increases the viscosity. Do you see the viscosity being thicker because of too many cells? Increases the viscosity, which will increase the resistance in the blood vessel. And as I said, if we're increasing resistance, our flow is going to be slower, right? Next one is blood vessel diameter. So for the diameter of the blood vessel, the size of a blood vessel is actually one of the most important factors in determining resistance, okay? This really can tell us how the resistance in the vessel is impacted. The smaller the diameter, the greater the resistance. Remember I told you, especially arteries can vasoconstrict and dilate, and that is very important because it could change where blood is going to, and it could also change what the blood pressure is, right? We always want to, we often fluctuate our blood pressure so that we can then change the flow and make sure that the flow stays constant, right? So the smaller the diameter, the greater the resistance. When I have a large diameter like this, and this is called vasodilation. This is a relaxation of the smooth muscle, dilation. Then my resistance, right, is going to be very low. This little cell over here, right, is happily going to flow through. If it's in this smaller tube, it's going to be harder to flow through one by one, go through this one. So this is called vasoconstriction over here. And this is a much higher resistance. It's harder to pass through this little tube because of the resistance, okay? And so one little note on this, okay, is that we have basically the blood vessels themselves do not generate the blood flow, right? The heart is creating a pressure and pushing it through. However, what the blood vessels can do is auto-regulate. They can vasodilate or vasoconstrict. Organs regulate their own blood flow intrinsically, meaning like themselves, by varying the diameter of the arterioles, okay? So this is based on the local tissue conditions. And we're going to take a look at different options as to why they might vasoconstrict or vasodilate, okay? So when a tissue is metabolically active, for example, you're running, right? And your skeletal muscles are in need of metabolism, right? Blood vessels, let's say near that muscle, will vasodilate to try to send more blood to that local tissue, right? It just makes sense. When you're using that tissue, you're going to send more blood. When you're resting and digesting, right? Remember the parasympathetic nervous system? You will not be using your skeletal muscle as much, and you'll send that blood to your digestive organs and your bladder and your all of the rest and digest organs, right? So this actually occurs due to local signals. So over here, right, you have your little vessel that's vasodilated. It'll dilate, right, due to a decrease in oxygen concentration, right? So when your tissues, like your muscles, start using up a lot of the oxygen around it, then that will signal to the blood vessels, hey, you should vasodilate so that we can send more oxygen to this tissue, right? The opposite is true, where if there's a lot of oxygen, then there won't be a need to dilate the vessel even more because the tissues can use up all of that excess oxygen that's there. pH can influence vasodilation. So tissues that are metabolizing a lot, right, that are undergoing and making ATP, let's say your muscles, right, they will increase their hydrogen ion concentration, right? So their pH will get lower, and that will signal a need to remove all this bad stuff. That will cause vasodilation, okay? So there's a few things, the measures of pH, right? But let's just look at the hydrogen ion. So when the hydrogen ion goes up, meaning the pH is low, that means that there's more metabolism and you should send more blood to that region. So we're going to vasodilate this blood vessel. Nitric oxide is also a substance that will cause vasodilation. This is released by endothelial cells to locally cause vasodilation. So that's actually another molecule that'll do so. And heat, increased heat. A lot of metabolizing tissues. Remember, when you use up oxygen and glucose and burn it to make ATP, that causes heat as a byproduct. So that can cause vasodilation also, to release heat at the skin surface. And lastly, hormones have various ways that they can go and cause it. Some hormones cause vasodilation. Some of them cause vasoconstriction. Okay, here you have some hormones. We actually talked about antidiuretic a bit, right? So this is some of the factors that can affect it. Now, last thing, so we talked about this very important blood vessel diameter that can affect resistance, right? Smaller meant more resistance. Now we'll talk about turbulence. Let's say, what is turbulence? It's the swirling action, right, that disrupts smooth flow of a liquid. And irregular surfaces can cause abnormal turbulence. Do you see these bumps here? Think of the bumps of turbulence if you're on the airplane, right? As blood is flowing linearly, nice and happy, all of a sudden it meets this and it bumps around, right? This liquid will bump around and create some turbulence here. So the greater the turbulence, the more resistance there is, right? And here's a picture. Do you see, this is a post-mortem specimen of a large artery. And you see that it's very smooth, right? So this used to be closed like a tube, right? This was a large artery. And look how smooth the inside is, right? And this is a patient that had atherosclerosis. So this is like plaque that builds up, fat and damage and inflammation to the vessel. This is the same part of the body, but a different patient. And do you see all of these bumps, these fat deposits? That would create turbulent blood flow and actually slow down the blood. It would increase resistance a lot and slow down the blood flow. So this would increase resistance. The more the turbulence, the more slower the blood will flow because of an increase in resistance. So I want you to pause the video now and try to answer this question. Imagine two individuals sharing a thick, viscous milkshake. One drinks from a broader, shorter straw, and the other from a thinner, taller straw. Which individual encounters the most resistance? Okay, so pause your video. And so over here, this is going to be shorter and bigger in diameter. Think of you if you're in a tunnel and you're walking with a certain amount of people and you're going through a bigger tunnel, right? That's shorter. You will go more at ease through it. It'll be easier, right? This is less resistance. This is a decrease in resistance. Whereas over here, if you have the same amount of people and you have to go through a very long tunnel that is smaller, where you could only go single filed, you will become claustrophobic, and this will be an increase in resistance, right? You guys will probably not get through the tunnel as fast because everybody needs to go in single file. There'll be a bit of traffic, right? Imagine this is a highway with like 6 lanes and this is one with 1 lane. Then this will have an less resistance. This one will have more resistance in it, okay? Now let's talk about bulk flow. This is basically what's happening at the capillary. What is this exchange at the capillary, right? So first I want to talk about this idea of perfusion, right? Perfusion refers to the passage through blood vessels and into the organ or tissue, right? If I say I am perfusing a tissue, it means that there is passage of these substances to the tissues, from the blood to the tissues. Nutrients and wastes are dissolved in fluid and they need to move in and out of the capillaries, right? So things like nutrients and oxygen, right? They first start in the blood vessels, in the plasma, right? Between the blood cells. They're in the plasma and they move out through the endothelial layer, the capillary wall, into the interstitial space, right? And then into the into the intracellular fluid inside of the cells, right? They get into the cells. So over here, right, you see water, glucose, amino acids. They go out of the plasma into the interstitial space and then into the tissue cells. Same thing for oxygen, right? Waste and CO2, they go through the opposite way. They go from the intercellular fluid, right? This is all the waste from metabolism, from burning glucose, using oxygen, making ATP. You make a bunch of waste like CO2, let's say. Here you see carbon dioxide, waste, water. All of this gets exchanged here and goes back into the blood vessels. So from the intracellular fluid to the interstitial fluid to the plasma, right? So we're going this way back into the capillaries. So here's the arterial end of the capillary and here's the venous end of the capillary, right? And so we're taking some things, putting them to the cells, and taking the bad stuff and putting it back into the blood. I want to review a bit of concepts that are important for us, the concepts of diffusion versus osmosis. So in diffusion, right, a solute, when we say something is diffusing, it's because there's a solute that can cross a cell membrane and move down its gradient, right? So over here you see this high concentration and this low concentration, and you see that the molecules do have an ability to pass across this membrane. We say that the membrane is penetrable because these molecules can cross through. And so the high molecules, right, will move out into this region and counterbalance so that there's equal amounts on each side, right? It's just like when you put milk in one part of your coffee, it ends up diffusing across all the coffee, right? Because it's concentrated in one region and then it diffuses away into those regions where it's not found. Osmosis is a bit different. This is when a solute cannot move. So over here you see the membrane here. These solutes cannot move. Look, 1, 2, 3, 1, 2, 3. There's no movement. And if you count these, there's about 10 here, and there's the same 10 here. They could not move across the membrane, right? Instead, if those solutes can't move, a solvent will move to the area where the solute concentration is highest instead, right? So the solvent, the water in this case, will move so that it can re-equilibrate the concentrations, right? This is like a very dark coffee, and this is like a very light coffee with 3 little caffeine grains. This is 10, right? So concentrated coffee, low amounts of coffee. If you took the water in this coffee over here and transferred it to this side to dilute this side, then you'd have 2 coffees on each side that are the same concentration, a medium concentration, right? I know there's less coffee here and more coffee here, but they'd be the same concentration. The solvent, the water, moved to this side to dilute this side. And look, now all of a sudden we're balanced. This is called osmosis. It's the movement of water, the solvent, so that the solutes become concentrated. And the reason why water needed to move was because these molecules could not cross the membrane. We're going to use this in a minute. So here's the picture that you should be familiar with. We're going to talk about the capillary pressures. So substances are exchanged in the capillaries due to 2 counteracting pressures. There is this pressure, this filtration at this part, and there's reabsorption. And basically, net filtration pressure, the ability to move things across the capillaries into the tissues, right, is dictated by 2 specific pressures, the capillary hydrostatic pressure and the colloid osmotic pressure, okay? We're going to see each of these one by one. But over here, right, this is the arteriole. And we call this end over here the arterial end of the capillary. And this is where filtration occurs. Do you see this arrow here? The gray one? This is a net filtration. The substances, right, will actually move out and filtrate into the tissues at this end of the capillary, at the arterial end. Whereas at this end of the capillary, you're actually going to have what we call reabsorption. Things will be reabsorbed back into what we call the venual end of the capillary, or the venous end, right? Because this is near the artery, this is near the vein. This actually matters that this is the arterial end and this is the venous end, because first we will see that here we're filtering out a bunch of stuff to give those nutrients and oxygen to these cells, and we reabsorb whatever is needed back, including all the wastes and bad stuff that we need to send back to the heart, okay? Now I'm going to talk about these 2 pressures, right? I told you to just look at the gray arrows to see the net direction where things are flowing. But these gray arrows, the net filtration pressure, it depends on 2 forces, okay? So in this case, when it's filtration at the arterial end, it's driven by the capillary hydrostatic pressure. Do you see this CHP, right? So capillary hydrostatic pressure is also known as just the filtration pressure. This is basically the blood pressure. Okay, so the heart, remember the heart squeezes and puts a pressure into the straw, right, into the vessels. That pressure is this CHP here, right? The capillary hydrostatic pressure is however much pressure is in the hose, which resulted from the heart contracting, right? So at this end over here, water and small solutes can actually be forced through the capillary walls out of the capillaries into the tissue. So water and small solutes will be pushed out to feed these cells, right? And actually larger solutes like proteins and red blood cells, let me actually draw a few red blood cells here, right? Here's some red blood cells. And also let me draw albumin. Do you remember albumin? That was that plasma protein. It's huge, right? This plasma protein, albumin, right? It's going to stay inside. They cannot pass through the little pores over here. So that's the situation that we have over here. So these will stay in, but the pressure, right, the blood pressure, the capillary hydrostatic pressure is able to push. Do you see this big arrow? It's pushing out into and filtering out those things. Meanwhile, the larger solutes, the proteins, they stay in the bloodstream. One thing to note, there is an opposing force. We're going to see this is the osmotic pressure, but it is pulling back. It is bringing things back in, and it's smaller. So actually, the capillary hydrostatic pressure is winning. Capillary, because it's at the capillaries. Hydrostatic, hydro means water. It's the blood pressure. Blood is mostly water. And so this is, again, remember the heart, right? This is not a real heart. But when you have the heart like this, right, it sends this tube, and when it squeezes, it pushes and creates, the heart squeezes and creates a pressure on the blood and pushes that blood. Well, that's the CHP. That pressure, right, will push on the water and solutes out, and it will send it into the cells. Now, the other situation on this end, on the venous end, is called not filtration. You're not filtering out all this stuff into the tissues. You're reabsorbing things, okay? So you're reabsorbing a lot of the stuff that you need back into the blood. So this is a result of the osmotic pressure. Do you see this arrow here, OP? It's much bigger than the capillary hydrostatic pressure. Some people call it blood colloid osmotic pressure. Colloid just means these bigger proteins. So this is caused, why is it that this happens? Do you remember that I said that albumin and red blood cells, albumin and red blood cells, right? They are found in the blood here, and they're too big, right? I'll make them a bit bigger. They're way too big to be pushed out into these tissues. So they stay here, right? But what happens again? So here you have the water that went out. What happens when you have a bunch of solutes, right? These suspended plasma proteins like albumin, antibodies, and fibrinogen that are too large to cross the capillary walls, is that they create an osmotic pressure. They create this situation. There's a lot of albumin, fibrinogen, and globulins here, and not many on the other side. They cannot cross, right? So instead, what will happen is water will move to the other side, and here water moves by osmosis to the other side to try to counterbalance that concentration. And so that's what's happening here. A lot of water is going to come back into the capillaries at this end. So water enters the capillary over here, right? So that's the idea that we have. We're going to go through each of these one by one. So first one, capillary. Let's look at this over here, the capillary filtration pressure, right? Also called the capillary hydrostatic pressure. This is the movement of water, right, through the capillary pores due to mechanical forces, okay? So this pushes fluid out into the interstitial space. I want you to look at these. This is our capillary filtration pressures, okay? And along the capillary here, you see that we have different amounts, right? What is it determined by? It's determined by, most importantly, this is the only thing I really want you to focus on. It's focused on the arterial and the venous pressures, right? basically over here, whatever the heart's pressure was, right? Whatever the pressure was as these that the heart squeezed at, that's going to be the pressure that's along these. And remember, at the beginning over here, the pressure is like 100 millimeters of mercury, right? And then along lower, right, over here at the capillaries, we have a pressure of about 35 millimeters mercury. Let me go back and remind you about this. I think it's important for us to see over here. Remember I told you at the beginning over here, we have about 100 millimeters of mercury in the heart, the pressure that it's generated. And then as we get to the capillaries, I told you that it's 35 millimeters mercury at the arterial end. And at the venous end, it's about 18, right? So we see that over here. We see 35 at this end and 18 at this end over here, right? So basically, this is determined by this. It's determined by the precapillary arterioles and postcapillary venules resistance, whatever. It's whatever resistance there is here. And the force of gravity to counter it, whatever. So what I care about mostly, though, is you understanding that this capillary hydrostatic pressure is the same thing as the blood pressure. It's the blood pressure specifically in the capillaries. And I want you to know something important. Remember I told you the pressure at the beginning of the tap of the garden hose is very high. And as it goes down the garden hose, it gets lower and lower and lower, right? At the veins, it's very small, right? Well, you even see this across the capillary. Here, at this part of the capillary, it's 35 millimeters mercury at the arterial end of the capillary. Mid-capillary, it's about 25 millimeters mercury. And at the venous end over here, it's 18, okay? So I want you to know that it goes down as you go through the capillaries. And then even in the venule, it'll be even lower. And then in the vein, it'll be even lower. It'll get to 2 almost, right? And I'll tell you why this is important soon. So the capillary hydrostatic pressure, right? Think of the pressure pushing against the walls of these vessels, right? Pushing over here. That's what's going to cause the blood, the water, and the solutes to flow out into the tissues, right? It's going to push against this wall. Think of the water pushing against the wall. Here it is, capillary hydrostatic pressure, pushing against this vessel wall. And it's pushing all of this water and small solutes. Look at glucose over here, right? Look at the ions getting pushed out, right? It's pushing all the water, glucose, ions into the space where the tissues are, right? What is staying in the vessels are these blood proteins, right? Like albumin or fibrinogen and globulins, right? So over here, you see that water, right, is going to be going through. Small solutes will also be going through the endothelial walls and go through onto the other side. The other pressure is called the capillary colloid osmotic pressure. Some solutes in the blood are called plasma proteins, right? So, mostly the one that's the most important is albumin. It's a big, chunky plasma protein, and they're way too large to even move through the capillary, right? Remember I told you these are big proteins over here, right? And they're way too big to go across, right? The smaller solutes, they'll fit across the membrane over here. Think of these little spaces between the cells. This is never going to pass through, right? So over here, these are too large to move across the capillary wall pores, and they'll generate an osmotic pressure. They'll generate a pressure on the water, right, that is constant throughout. So here, these are not moving, right? But whatever water is on this side, since there's a high concentration of albumin here and almost no albumin in the tissues here, this will actually be pulling water back into the vessels, the blood vessels, right? So if you take a look over here, right, I want you to notice that this osmotic pressure is constant throughout, because the amount of proteins don't change, right? The amount of albumin doesn't change here versus here. They're all flowing through the blood equally. And the concentration of proteins is higher in the plasma compared to the interstitial fluid, right? So here it's much higher the amount of albumin compared to over here. And so this concentration being different, right? The plasma is said to be hyperosmotic. It has a lot of osmotic pressure, a lot of albumin, and this will pull water back into the vessels. Do you see this arrow here? 25 millimeters mercury. That is the blood colloid osmotic pressure, the capillary colloid osmotic pressure. It's pulling back water equally across the membrane, right? It's counteracting actually this force here. And it's pulling back because these solutes cannot move. So water will want to come back at a certain level, right? So the capillary colloid osmotic pressure is 25 at this end, 25 at this end, 25 at this end, because albumin is the same level over here, the same level over here, and the same level over here, right? So we're good with that. Now, I want us to now piece this all together, right? Remember I told you that substances are exchanged in the capillaries due to two counteracting pressures. You have the capillary hydrostatic pressure and colloid osmotic, and together they make the net filtration. They decide the net pressure where things will go, right? So at the arterial end of the capillary over here, the capillary hydrostatic pressure is 35. It is bigger than the colloid osmotic pressure, which is 25. Therefore, our net filtration pressure is said to be positive. The net filtration pressure, look at this, 35 minus 25. That means we have 10 going in this direction, right? This pressure, if this is tug of war, this pressure is winning, and you will have more substances going out and filtering out into the tissues at this end over here. So fluid leaves the capillary and enters the interstitial fluid at this end of the capillary. This is called filtration, right? At this end, however, right, at the venual end of the capillary hydrostatic pressure is 18. Why? Because remember, as you go down a hose, the blood pressure goes down, right? Because you're losing energy as you go out and it dribbles at the end. So here, 35, 25, 18, it's lower, right? And so because the capillary hydrostatic pressure is lower than the colloid osmotic pressure, which is 25, if you do 18 minus 25, that gives you -7, right? So all this to say, this pressure is winning, the osmotic pressure is winning the tug of war, and it's reabsorbing things. Fluid is going to be leaving the interstitial space and going back into the capillaries with all that waste, right? And so this is reabsorbing the water and all the wastes. So here I deliver my glucose and my what is needed, the solutes, to the cells. And here I am picking up the wastes back and putting them into the venule, right? The last thing I need to tell you about, okay, is do you see over here how we filter out 24 liters per day here out into the tissues, and we reabsorb 20.4 liters per day? There's some fluid that we don't pick back up, right? Because about 3.6 liters per day flows into the lymphatic vessels and goes back into the circulation, right? So what is the lymphatic flow? Excessive fluid and escaped proteins are not always reabsorbed by the capillary, right? They're not always brought back and reabsorbed. We see actually there's about 4 liters a day that isn't, right? And instead, they're returned to the venous circulation by the lymphatic system. So next to the tissues and next to all the capillaries are a separate set of tubes that are called the lymphatic vessels. And we're going to see them in the next system. But the lymphatic vessels, I like to think of them as the drain of the sink, right? There's a bunch of things that happen in the sink over here, but then in the end, any excess water, all the rest will just go down the drain, and they'll actually be returned to circulation. They'll be filtered out and returned to circulation. So it'll be brought back to the heart eventually, right? So it's very interesting because this lymphatic vessels, right? They are like the drainage system. When pressure is greater in the interstitial fluid than in the lymph, right? This is the substance in here is not blood, it's called lymph. So when the pressure is greater in the interstitial fluid over here, right, compared to the lymph over here, due to an accumulation of fluid in the interstitial fluid, the pores of the lymphatic vessels, these little pores, they allow fluid in, but not back out. It's a one-way valve. So they go back into the lymphatic vessels and they go around and they get drained back into the circulatory system eventually. Interestingly, if you have blockages of lymphatic vessels, of these lymphatic capillaries, then this might cause edema, right? Imagine you have all of this fluid that could drain out into the lymphatics, but all of a sudden this is blocked. You're going to have 4 liters a day start accumulating in your tissues. And where's this water going to accumulate the most? At the lower extremities of your body, because gravity is pulling down, right? So edema often happens in the legs and the feet, right? That's an accumulation of these fluids if there's blockages in the lymphatic vessels. So look over here. This is stage 1 of edema. You have different stages, and it could even get to a point like this. This is not fat in the legs. This is fluid accumulated in the tissues, right? This is really not a good case, and you need some help for that, definitely. But that's what edema does. And if your circulation is not that great, then you might, some people need compression socks to help and prevent accumulation of fluid in the extremities. So that's our lymphatic flow. All right, so let's talk about the capillary exchange now. So I want to talk about this transition point between filtration and reabsorption that occurs over here. I really like this graph because it shows that the capillary hydrostatic pressure, the blood pressure, in a tube, as you go from the arterial end to the venual end, do you see how this capillary hydrostatic pressure goes down, right? That blood pressure, as you go down a tube, it gets smaller and smaller and smaller. You lose energy, you lose pressure as you go further in the garden hose, right? Whereas the colloid osmotic pressure stays constant throughout. The pull of water back, right? It is constant because the albumin is the same level at this end of the tube than this end, right? There's the same amount of albumin throughout the whole circuit. So I really like this because you see that at the arterial end, right? The capillary hydrostatic pressure is bigger than the colloid osmotic pressure. And therefore at this end, this pressure wins. And you have filtration. You have this arrow because this pressure is bigger than this one, right? This pressure is bigger than this one. So you have filtration out of the blood into the tissues. Then this goes down, and as you get to the middle-ish, closer to the venous end actually, of the capillaries, this is called the transition point because the capillary pressure, this pressure here, is equal to the osmotic pressure, and there's actually no fluid movement. At the transition point, there's no fluid movement because this pressure over here, 25, is the same as this pressure here, 25, so there's no net movement. You just don't see any gray arrow. No fluid is moving. However, it's interesting to note that only gases will exchange. This is actually where oxygen and CO2 exchange. Because remember, they just go out and they cross the plasma membranes. So they don't need to pass through the little pores, right? And then, right, over here at this end, right, at the venual end, you see that actually the colloid osmotic pressure, the osmotic pressure is bigger than the capillary hydrostatic pressure all along here. and it just gets worse as you go further. So this is where the colloid osmotic pressure wins, right? This arrow, 25, beats this arrow of 18. And so fluid moves back into the capillaries at this point, right? So all this to say, right? Additionally, capillaries filter more than they reabsorb, right? Do you see over here it says that there's about 24 liters filtered versus 20.4 liters? So they filter more out, and that's why we need lymphatics to drain out that excess that is not resorbed. The excess fluid enters the lymphatic vessels for immunosurveillance, blah, blah, blah.